All right, welcome back everyone. We're going to move on with this idea of beam design from last time and expand the way we design our beams by looking at another important concept, which is deflection. So before it was how strong does the beam need to be. Now we're looking at after we pick the beam that would support that load, how much deflection will there be. And a lot of times this will actually govern which beam we can pick. So it's an important check in the process. So let's start by defining what we mean by deflection. So if I had a beam with this point load P being applied to it, you can imagine what's going to happen to this beam. It's going to make a big smiley face, right? So let's say that's like the midpoint of the beam deflecting down. Now the distance away from where it started is what we're calling our deflection. Basically, how far is it moved from its original starting point, right? And we're going to use the symbol y as the vertical y displacement away, that deflected value, right? Now there's one other term we have to be familiar with. This is green line that I have drawn here. That line has a special name. We call that the elastic curve. And basically what that means is deflection is your distance away. Elastic curve is like, it's like the shape of the entire curve. So what we're going to do is we're going to develop some equations, or we're going to look up some equations to define that elastic curve. And the reason we want to do that is we might want to say, instead of the deflection at the midpoint, what is it at 2 feet from the end? We'll do an example like that in a little bit. And then we would know the equation for that line, plug in 2 feet, we'd have that. So for most cases, these deflections can be looked up in a table. So, for example, I'm providing this table in the notes section, and you can use it for any other problems you might have. But if I look here, what I have is a table which defines different types of loading, right? So let's look at this first one. This is like a cantilevered beam. You know, it's attached to a wall like a diving board style, and I'm placing a load on the very end, and of course the deflection would look like that, right? You can imagine what it would look like. So I can see this is that elastic curve I talked about, the shape of that deflected shape. I have this Y max, which is my maximum deflection. In this case, it would happen at the very end of the beam. I can see that, right? And then if I want to know what this value is, I have an equation. It says minus PL cubed over 3EI. So the P would be the magnitude of that point load. The L is the length of that beam, cubing that and then dividing by 3. E, we talked about E before. Remember what E is? E is that slope from our stress strain diagram. It's also known as the modulus elasticity, or Young's modulus. For steel, it's typically 29 times 10 to the third. I'll give you that in any problems we might have, but in standard units, 29 times 10 to the third is like your magic number. And then right next to the E, we have this I value. We talked about I as well. We said I was our moment of inertia, which could be, you know, 1/12 BH cubed, or if we have like an I-beam, when we sized them before, we can just look that up in a table as well, which we'll be doing today. So I know where all those values come from. I could find that maximum deflection. I could find slope at the end. That just means like if I were to continue this line along, what is the angle theta? So I could plug that in as well. And then the last column is our equation for the elastic curve. So like I said, if we could come up with an equation for this curve as a function of x, then we could just plug in these values for any, say I wanted to know the deflection at, I don't know, say 30 inches away from that support, right? Well, I could put in 30 there, put in 30 for my x's. Everything else is the same. L is still whatever the length of the beam is. E is at 29 times 10 to the third in kips per square inch. I would be the shape of the beam. So, so that's in general what these equations look like. Now, looking at the loading, I have a cantilevered beam with a distributed load for the second one. The third one is a moment. That means it's like we're twisting it around on the end. Same idea. The fourth one is a point load in the very center. So that's more like what I started off with, right? The fifth one is a point load, but not at the middle. Some other location. The sixth one is an evenly distributed load. This is probably the most common one that you should be familiar with, right? This would be the one that you use most often, because if you're designing a beam, usually you take all these loads and it ends up just being a distributed load. Like you start with the pounds per square foot, depending on your spacing of the beams, becomes pounds per linear foot, and that is the load on the beam, which means we have a distributed load over the whole thing. And then we have a moment if we had it supported on both ends, right? So those are the 7 cases that we have in this table. Let's go ahead and take a look at an example on how we would use this. So this example should look familiar. This is the exact same problem we did last time. So that's why it says continuing example from beam design. So if you don't remember this problem, go back to the last one. In the last problem, what we had to do is find a beam that would support this load of 1.67 kips per inch over 120 inches. And what we found from that problem was that we could support it with a W18 by 40. The next step in the design process would be say, well, how much deflection is there? So going into this example, what does it say? We say we have this 18 by 40 I-beam, steel I-beam. It's steel. We have a modulus elasticity of 29 times 10 to the third kips per square inch, as that magic number I told you for steel. And we need to just support that same distributed load, 1.67 kips per inch over the 10 feet. What we want to find is the maximum deflection for this beam. So once again, distributed load over the whole thing makes a big smiley face. We can imagine what it looks like. We know, well, we should know just from symmetry that it's going to happen right at the midpoint. But regardless, even if we didn't know that, well, all we need to do is come up to our table and say which one is this, and I see that that's case number 6. Like I said, probably the most common. So what I'm going to use here, up top it says maximum deflection. Well, that's the problem I was looking for, maximum deflection. It's this value right at the midpoint, right? L over 2. And its value can be found by using this minus 5W L to the 4th over 384 EI. So bam, there it is. Maximum deflection minus 5W L to the 4th over 384 EI from that table. So let's start plugging in values. I know what W is. W is that 1.67 kips per inch. I know what L is. That's the length of the beam. And if you forgot, you can come up here and say, what is L? L is the distance between my 2 supports, right? Well, in my case, that L is 120. I know what E is. It's given in the problem, 29 times 10 to the third. What I don't have right in front of me is this I value. What am I going to do about I? Well, I'm given that it's an 18 by 40. I found that from last time when we did I-beam sizing. And so we had a table last time that had all these I-beams. And from that table, we were using that SX value to determine this. But now what we care about is the value right next to it. It's I sub X. The reason it's I, and you can see there's 2 I's, IX and IY. The reason it's IX means that we're having an I-beam like you'd expect it to be loaded, right? Vertically down. For some reason, if you had an I-beam loaded sideways, then you would use the IY value. And for a normal beam, you just don't really have that. For columns, you have that, and for other cases. But for right now, for this section, we're always going to use the I in the X direction if we have an I-beam. Well, what I-beam did we start off with? I already forgot. 18 by 40. So I find my 18 by 40, I scroll over, and I see I have an I value of 612. The units are inches to the 4th. I'm trying to be nice with the units and not have you convert too much. So notice I have everything in kips and inches. Those are so if you had a problem and it had, like this problem started off with this being 10 feet, convert everything to kips and inches. That's just the most common units that you'd want to use. Otherwise, you have deflection in feet, which is a little bit weird. Actually, this is labeled Y. Another notation you'll see is a lowercase v. I usually use that, but I think Y is a little simpler, so we're going to use the notation Y, and it's Y in that table, right? So plugging in these values, then I have minus 5. The distributed load is that 1.67 kips in inches. Remember, those are the units, kips per inch. The length is 120 inches. I'm taking that to the 4th power. dividing by this 384, and then E, we said was 29 times 10 to the third kips per square inch. And then we have I, and we just looked that up, and I already forgot what it was. I is 612 inches to the fourth. So plug that all into your fancy dancy calculator, and I get a negative 0.254 inches. The negative, by the way, just means that it's going down, right? Positive up, negative down. Makes sense if I have all this load on there that it would go down. So just try not to drop that negative sign. It's real easy to do. So that's the simplest way we can use this table. Not too bad, right? But what if we had the same problem, but we didn't want to know the maximum deflection. Instead, let's say we wanted to know the deflection like 24 inches from the end. So let's do another example with that being the case. So this example looks almost identical to the other one. The only difference here is instead of finding the maximum deflection, I want to find that deflection 24 inches from the left-hand support. So I have it drawn in here, 24 inches from that left-hand support. What is this Y value? So once again, I go to my table, and now, too much stuff on here. Now, I'm not going to look at this maximum, because maximum takes place at one place, and that's right at that midpoint, right? Right there. Instead, I want the deflection 24 inches over it, some distance over. So this is where, if I'm going to do this, what I need to use is the equation for that curve. So that equation, that means that's an equation mapping out what is my Y value as a function of X. So this is the equation I'm using. It says what is my deflection Y as a function of X, you know, how far over. In that case, X would be 24 inches. So this is the equation I'm using. Let me rewrite it down underneath my problem. All right, so like I said, we're going to use that elastic curve, plug in 24 for X. There's the equation rewritten. And it's just a matter of plugging in all these values. Don't forget your negative sign. That load was 1.67. I'm going to drop my units because I know them all in kips and inches. I suppose you could feel free to do the same as long as you're sure all the units are the same. So I have 24. E is 29 times 10 to the third. We looked up I. We found I to be 612. And I'm going to do like a bracket so that I can put more parentheses, more mathematically correct, right? Now this X, what is X? X is that distance away from the end. In inches is 24 inches. So we have 24 to the fourth power minus 2. The total length is 120. That X, once again, is 24. Now I'm cubing it. Plus the length, 120, cubing that. X, 24. Just a lot of stinking algebra, right? Be careful punching this in the calculator, getting all your parentheses in the right place, order operations, whatever. You might want to do it in multiple steps and then write out different values, whatever it takes. I know this is a big, big, long equation, but if you did plug it in, you'd end up with negative 0.15 inches. And, of course, that is less than the maximum, which would make sense, right? If we think about the elastic curve, what we found over here in this midpoint was, I forgot what we found. What did we find? 0.254 minus 0.254 inches. So, of course, you'd expect it to be less because I'm closer to the end, and it is indeed less at 0.15 inches. So the last little thing that I want to cover today is this idea of what I'm going to call a table trick. This table trick, also known as superposition, is the idea that we can add deflections together. Technically, we could even subtract them if I have one going the opposite direction and things like that. So here we go. We can add deflections from multiple loads together. This is also called superposition. And I think the best way to see this would be looking at yet another example. So let me draw that out. So we're up to example 3. It's the exact same problem we've been working all along. The only difference, and I wrote it in blue, is we are going to add another load into it, right? So we still have that 1.67 kips per inch distributed load, but now I have an additional load of 100 kips at the midpoint of this beam, right? At that 60 inches away from the support. So I'm still trying to find the maximum deflection. So that'd be the deflection right at the midpoint. So if I come up to my tables once again, so we still have this distributed load. I want to know the deflection maximum right at that midpoint, so I can use that maximum deflection equation, 5WL to the fourth over 384EI once again. But now I'm adding a point load. There isn't a single scenario on here where it shows both, right? But I can add these together separately. So then I have my point load of minus PL cubed over 48EI. So two equations, I can add them together. For the first one, I get the exact same thing, same numbers, so I'm going to get the negative 0.254 inches again. And then adding in the second one for the max deflection due to that point load, I see it's minus PL cubed over 48 EI. And plugging in my numbers, what is P? P is that point load. We're supporting 100,000 pounds or 100 kips at that midpoint. Big numbers, right? Minus 100. I'm going to get a little sloppy with my units because I know I'm in kips and inches again. The length is still 120. It's in inches. Cubing that, divided by 48. E value, we said it was 29 times 10 to the third. We have the same I-beam, so the same I value, forgot it again, 612. And plugging all that in, I end up with something like minus 0.203 inches. So the key to this idea of being able to add them together, this superposition, is now I can find my total deflection at the midpoint, my worst case. And I can say that total deflection Y is equal to Y from my first load plus my second load, or negative 0.254 minus 0.203 for a total deflection of negative 0.457 inches. And when you get into the structures course, you'll talk more about requirements. Typically, there's this requirement, and you'll see this often that this is like extra. I'm not going to have this in this class, but often this needs to be less than or equal to the total length divided by 360. And is it? We could check this, because if it isn't, we'd have to pick a different I-beam that's a little stronger. So our total length for this I-beam is what? 120 over 360, 0.33. So I would have failed this requirement, right? Meaning that if I were doing this in real life, what I could then do is repeat the process, but I could work this backwards and actually solve for what I need. What is my minimum I value I need to support so I don't have maximum deflection? Because like I said, it's more than the strength of the beam. The deflection oftentimes will be the governing factor, right? If I could figure out what my I required is from these equations, then I could go into these tables and say, what is my I? Same idea, finding the lightest I-beam based on these I values, right? Making sure it's a minimum of whatever it needs to be. So like I said, I'm not going to really do that in this class, but for those who are thinking forward to structures, my guess is you're probably doing something like that. And just in general, it's good knowledge. So as usual, I hope you found that helpful, and I'll talk to y'all later. Thanks.